So as we move into 6.5, we start to work with what we call the properties of logarithms. So again, some things to pick up on as far as the properties of logarithms is we'll have, these are the most common properties of logarithms that we have as properties. Where they actually come from are from the properties of exponents. So if you look at these down here, the product of powers, notice how if we have a to the m times a to the n, so if you have the same bases, you can simplify this by keeping the same base and adding the exponents. So if I had 3 squared times 3 to the 5th power, notice that's the same thing as 3 to the 2 plus 5, or in other words, 3 to the 7th. So notice how if we have a power of a power, if we have a to the m to the n, notice how that's going to be a to the m times n. So we have that property. Another common one is the negative exponent. If we have a to the negative m, we talked about this. That's the same thing as 1 over a to the m. And of course, a to the 0, anything to the 0 power is equal to 1. So remember, 0 would be the input and 1 would be the output. So if we're doing logarithms, if we take the log of 1, the log of 1 should be 0. That should reverse itself. Notice also the quotient one. If you have a to the m divided by a to the n, the property of exponent says if you have division involved, you could simplify this by subtracting the exponents. So if I have 3 to the 5th raised to 3 to the 2nd, notice that this is 3 to the 5 minus 2. So there's subtraction involved. So if you look at some of our logs up here, properties, notice that if we have the log of 1, it doesn't matter what the base is, that's going to be 0. So that's a property that we can take advantage of. So again, properties are things that we memorize. So another one we have is the log of a base a is equal to 1. Or if we have the log of m to the r times the log of m raised to the r power base a, notice how that's going to be r times the log of m base a. So this property here becomes rather popular for us, is if what we're taking the log of is raised to a power, that power can come out as a coefficient or a factor, if you will. It's going to be multiplied out in front. Some of these properties here are coming from composite functions. So if I look at these two properties here, they're going to be created by composite functions. So enough said for the time being. Let's look at our example that we're asked to do. So it says use the properties of logarithms to find the exact value of the expression, and it says do not use a calculator. So notice that there's actually two functions here. There is the exponential function, which would be f of x equals e to the x, and the second function is g of x equals ln of x. So notice how these two functions are involved. So if we do a composite function of these, if we do g of f of x, so in other words, e of x goes into the g function for x. So in other words, we have g of e of x, and notice how this x here gets replaced by the e of x. So we end up with this natural log of e to the x. Since f of x and g of x are inverses of each other, we know that g of f of x has to equal x. So in other words, our answer has to be whatever x is here. So if I look at this problem, the natural log of e to the negative 3, since these are inverses of each other, the answer is just simply going to be the exponent of what we're taking the log of. So the answer would be a negative 3. So if I type it into the calculator, the natural log of, if I type in second e, raise it to a negative 3, and close my parenthesis, that answer should be just simply negative 3. Oops, I actually got to put it in the right spot though. I was graphing it. So the natural log again, whoops, the natural log of e to the negative 3. Notice how that does give me a negative 3 as an answer. So this actually comes from these being composite function. So the answer is simply what x is. In other words, what this exponent is right there.